lesson 1.6, solving systems of equations and inequalities. We're going to be solving by graphing for this. Today our focus, our learning target, is able to solve a system of linear equations by graphing. And our secondary learning target for day one is solving systems of inequalities, also by graphing. So this is day one of Calc-Path Geometry, lesson 1.6. Systems of equations. Systems of equations, let's look up a formal definition, but basically it's two or more equations. Let me minimize this. System of equations. We'll summarize it on our own in a second. System of equations is a set or collection of equations that you deal with all together at once. Linear equations, one that graphs straight lines, are simpler than nonlinear equations, which we'll be learning some in this class. You'll learn more of them in Algebra 2 and in pre-calc. And the simplest linear system is one with two equations and two variables. So does an equation system with at least two variables, a set of equations, and you can't see that, a set of equations with at least two variables, set of two or more equations with at least two variables. And in Algebra 1 and in Algebra 2, you deal with systems of two equations with two variables. When you get to pre-calc, you'll look at systems that are larger than that. And so we're looking for a solution. The solution to this system is a point or points. When they're both linear, there's just a point. Points that make both or actually make all equations true. So we're looking for a common point that they share that makes all of the equations true. So in our first example, we're solving the system of equations by graphing. So it's as simple as graphing the two equations and looking for where they intersect. So in our first example, we have y equals the opposite of x plus 4. This is in slope-intercept form, so I start at a y-intercept of 4, and I go down 1, right 1. And I just continue the slope all across the entire graph. And I could also reverse this up 1, left 1 to get the same slope of -1. So there's my line. I have all those exact points. You really should use a ruler. I'm going to grab one in a second so you can be very precise at seeing where they intersect. My next equation has a y-intercept of 2 and it has a slope of -3/5. So I'm going to do down 3 and over 1, 2, 3, 4, 5. Hey, I already have the solution. Down 1, 2, 3, and over 1, 2, 3, 4, 5. So there is my second line. I have at least 3 points to connect. The more you can connect across the graph, the better. But we already have our solution, so I'm not as concerned about it. The place that works, that point that works, is 5, -1. 5, -1 is my solution to this system of equations. And when I plug that in, and this is how we're going to check, -1, does it equal the opposite of 5 plus 4? Yes, -5 plus 4 is -1. -1, does it equal -3/5 times 5 plus 2? So I'm basically plugging the 5 in for the x of both equations and the -1 in for the y. This is going to be -3 plus 2 is -1. So yes, this point is the solution to both equations, and I could see it on the graph. It is the point where they intersect. So when we solve by graphing, we're looking for the point of intersection. I'm going to write points only because there are some functions that are not linear. We'll deal with those later in this course. Well, one of them. The rest you'll deal with in Algebra 2. Points of intersection, or points that make both equations true. The next one is actually in standard form. So to graph this, I'm going to find the x and y intercepts. For my first equation, and I'll do that one in blue, I'm going to find my x-intercept. So when y is 0, I have x equals -3. So -3 comma 0. And my other point, when x is 0, divide both sides by -1, y is +3. So -3, 0 on the x-axis, 0, 3 on the y-axis, and connect the 2 points to get my line. You could also solve for slope-intercept form, but this is a much more time-efficient way for the way that these are, since they're already in standard form. When the y variable is 0, I'm left with 2x equals -6. Divide by 2, I get x equals -3. So -3, 0 for my x-intercept. Hey, that's nice. And 3y equals -6. Divide by 3, y is -2. So 0, -2. And I don't have to worry about looking for the point of intersection because I already found it. It is -3, 0. It's a point on both, and if I plug it in, I know it makes it true. -3 minus 0 is -3. -6 plus 0 is -6. So we have the correct solution. Our next example of graphing linear equations actually comes from letters A and B. So take a moment to pause the video and try these two problems, see if you can graph them and find the solution. Welcome back. If you graphed letter A correctly, if you want to see if you got it right, you can fast forward the video. But if you were graphing correctly, you would have started at -3. You go up 1 and over 2 and continue this pattern until you have all the points that you could get on this graph. And I might just connect those now and double check that I have the right points later. If I need to, I can check some points over here. The other one is in standard form, so my y-intercept is 11, which unfortunately is not on my graph. I'm going to have to add 1 tick mark. I could have rescaled this if I hadn't had it labeled already. And my x is 11/3. That's a little trickier. So because it's like that, and I don't like that very much, I'm actually going to use slope-intercept form. We already know the y-intercept is 11. I could just find the slope, which is going to be -3 over 1. But if we're not sure, we could solve for y. Y equals -3x plus 11. So from 11, I'm going to go down 1, 2, 3, and write 1. Down 3, write 1, down 3, write 1, down 3, write 1. Hey, there's where they intersect. And so now I'm going to connect those. My point of intersection is 4, -1. That's the solution to the system of equations. Now I do have to check my answer by plugging it back in. So -1 gets plugged in for y. So is -1 equal to 1/2 times 4 minus 3? Well, that's 2 minus 3 is -1. And for the other one, I'll do that right here. 3 times x was 4, plus y, which is -1. Does that equal 11? Well, that's 12, plus -1 is 11. So I checked my answers. You do need to check to make sure you have the correct solution. If you graphed letter B correctly, you have the line y equals x, which has a y-intercept of 0, and then you go up 1 and over 1 for each of those points. So you plot those points and you connect them with a straight line. And then for our other equation, this one I'm going to do x-intercept. 15 divided by 3 is 5, so 5, 0 for my x-intercept. And I'm not as concerned about this fractional value because it's going to be 0.5. It's going to be 15 divided by 2, which is 7.5. So 0, 7.5. I can be a little more accurate with that by going, if it was 1/3 or 1/2 or something crazy like we had on the other page, then I may actually put it in slope-intercept form. And I'm going to go to 5, 0. Hey, there's 5, 0. Here's 7.5. And I connect them, and there we go. Our intersection point appears to be right here at 3, 3. So I plug in 3, 3 to both equations. Does 3 equal 3? Of course it does. Does 3 times 3, which is 9, plus 2 times 3, which is 6, equal 15? 9 plus 6 does equal 15. So we've checked our solutions. This concludes learning target 1, being able to solve a system of equations by graphing. You graph the two linear equations, you find the intersection point, and you double check by plugging it back in to make sure that that point, that x and y value, are solutions to both equations. Please tune in to the next video clip for solving systems of inequalities.